Hello learners, welcome to Education Online program. I'm teacher Willa Lucia. So in our previous lesson, we learned about distance time graph. Because we say there were two types of graphs, you can describe the movement of any object in those two graphs. So we looked at the distance time graph where we talked a lot about it. We looked at when a body is moving with a constant velocity, how will it look like in a distance time graph? When the body is moving with a non-uniform velocity, what happens? We also saw what happens when the body is coming back to rest. So today basically we shall be learning about the velocity time graph. Velocity time graph. So how is this velocity time graph? What are the features of this velocity time graph? So when you look at velocity time graph, for it shows the speed with which an object is moving and to what direction is this object moving in a given time interval. So that meaning that when you're drawing the velocity time graph, there is the y-axis will take the velocity or the speed the object is moving with, and then the x-axis will take the time interval for all the journey of the body. So let's look at how this x-axis will look like and the y-axis. They are not different from what we saw in our previous lesson when we were drawing the graph for the distance and time. So this one is just like that, because we have the y-axis, which is the vertical line, and then we have the x-axis here, which is the horizontal, like that. So you'll see that with the velocity time graph, you will have the velocity on this axis here, but you remember not to forget the SI unit. You keep it here also in meters. So our velocity is measured in meters per second, and then we have the time right here, which is measured in seconds. So you find out that with this velocity time graph, what happens is that after getting it, because there are going to be very many lines, different lines you use for describing this motion. When the object is moving with a uniform velocity, how will the graph look like? When it is moving with a non-uniform acceleration, what happens? So those are some of the features of the graph. So you'll see that in the graph you can find a steep line. So this steep line, what does it show? So also there are curves in the graph. So when it is the curve, you find out that the body is moving with what? With non-uniform acceleration. So let us take a look at some of these lines I'm talking about. So we have the uniform velocity. Uniform velocity. When the body is moving with a uniform velocity, you find out that the body will have, in your graph you represent it with a horizontal line. So when I mean horizontal, it looks like this, moving this way. This one becomes a vertical line. So this in a graph, in a velocity time graph, will give you it will show you that this body is moving with a uniform velocity, which is not the same case with the distance time graph. So if you want to draw that, explaining to someone that your object or your car is moving with a uniform velocity, instead of writing it in words, you just draw. You have your Cartesian plane, since we say that you have to have the time factor on the horizontal line, so this one is our velocity in meters per second. What happens is that, you see, this one is also a horizontal line. It doesn't mean that where this horizontal line is where you say the body is moving with a uniform velocity. But then we introduce another line here. Because this one carries the x-axis, it is going to be carrying the time interval you're taking for the body to move from one point to another. So this one here, this horizontal line here will show you that this body is actually moving with a uniform velocity. So when a body is moving with a uniform velocity, what actually happens? So you see that with the when the body has already attained that uniform velocity, the initial velocity the body started the journey with is equal to the final velocity. I mean the velocity the body is going to come to rest with. So that means that here, this velocity right here, which is the initial, will be equal to this one here at that point. So that means that the body is displacing, is covering a distance, equal distance at equal time interval. That is with the uniform velocity. So we have another graph of uniform acceleration. Uniform acceleration. So what happens when the body is moving with uniform acceleration? Since we say from the definition of acceleration, we say that it is the rate of change of what? Of velocity with time. So if it is like that, when the body is attaining this uniform acceleration, you find out that the initial velocity the body started the journey with will not be equivalent to the final velocity the body will attain when it is moving with uniform acceleration. So you see that the line of uniform acceleration is actually moving it this way. You have it like that because there the body is covering a distance, but then the distance the body is covering is not equal with time. So you see that when the body moved this distance from right here up to here in 3 seconds, it's going to cover more distance as the time elapses. So let us see how we shall indicate the uniform acceleration on our velocity time graph. We shall have it like this. Where we have our velocity here in meters per second, then we have our time. So this here indicates a uniform acceleration. For our case here with this graph here, we assume that it starts from rest here, from the 0 point. So when you see that line there, it indicates a uniform acceleration. So we still have more of that, or we have the uniform deceleration. So with uniform deceleration, what happens? When we are talking about the deceleration, we are talking about the body coming to rest. You can also find it as, instead of deceleration, they will say the body is retarding. So how will it look like in the graph? We have our uniform deceleration. So for the uniform deceleration is going to be looking more of the uniform acceleration, but then this one with the uniform deceleration, it is going to show you that it's in the opposite direction to uniform acceleration. So we shall have it this way. So you see that steep, it is actually sloping, coming back downwards. So let's not forget that. And then our time here. The difference between the uniform acceleration and uniform deceleration is not only that they are moving in the opposite direction, but then you'll find out that with the uniform acceleration, this elevation here of the light comes with a positive, but then the deceleration here, the body is moving in the opposite direction. Like if you move from home to town, then coming back, moving from home to town, we are giving it the positive sign. Then what if now you're coming back from town back home? You see that you're using the same street, but then this time you're turning, coming back there the opposite way, so giving it a negative. So you find out that with deceleration, when you try to calculate the deceleration of the body, you'll find out that the figure, you mostly get it as a negative. So that negative shouldn't be scaring. It is just because the body will be moving in the opposite direction. So we have the non-uniform acceleration. Our non-uniform acceleration So with this non-uniform acceleration, you find out that the body keeps on accelerating at a different rate. It keeps on changing the velocities with time. So how would it give you? So with the non-uniform acceleration, instead of you attaining a straight line, you will be getting things like a curve. So you'll see that instead of you having this line, you're going to be having something like this. This is our time, and then the velocity. So instead of you attaining this line as the uniform, because the body is accelerating non-uniformly, you will get curves like that. It can reach a point and then changes again like that. So what happens is that with this, you can still get the slope of that, because in the graphs, all what we've drawn here, we can still get the slope of that graph. We shall see how we do that. So you see that all these graphs here can be combined to form one graph, not including the non-uniform acceleration. But then if you check the uniform velocity, uniform acceleration, and the uniform deceleration, all of them have straight lines. That means that in linear motion, when the bodies have got straight lines like that, it becomes so easy for you to combine, to explain the whole motion of this body into one single graph. Let us see what we shall get when we combine all what we have here into a single graph. Let's take this one right here so that we see when we are combining it whether it is actually going to fit in that graph. That is uniform deceleration. So we keep it this side. Okay. This is not a different one. We are just trying to, we want to rub this so that we see how we are going to fit, how we're going to fix all these three in a single graph. So combining that, this is what we shall end up with. We still have, because if we check our graphs, on the y-axis we all have the velocity there, and then on the x-axis we have the time on each and every graph we drew that side. So let's now pick them and put them together. So we are going to start with the uniform acceleration. When the body is moving with uniform acceleration, it can start from any point here. It is not a bus that it will be starting only from the 0 mark, from rest. But you can find out that it can start from somewhere up here when the body had already attained. The body has been given some kind of velocity, initial velocity. So, but for this case, we are going to assume that our body is at point O, which is at rest. So we are giving it a uniform acceleration. We pick that. Since we say it will be moving like this, with a straight line there. Then we come and check which other can fit so easily. Could it be this one? Could it be that? Or which one, so that we can explain so easily. You see that instead of putting this, if we come and say that the uniform deceleration is direct here, then this one, it is also fine, because there you can still explain your graph, meaning that your graph first accelerated, moved with a uniform acceleration, then it came back to rest. But then let us see, what if now the body attains a uniform velocity? So we shall have it right here. So if you look at your uniform velocity there, here the body was already starting from some point already, from the y-axis, if you check that. But then here we are just connecting it direct, that after it accelerating uniformly, immediately it was given the uniform velocity, displacing the same distance, covering it in the same time interval. So we shall have it like that. Then the body comes to rest after all the movement. In case it does not come to rest, you never know, you also still move the body somewhere else. If you continue moving the body, you can still include it this side here. To move, you accelerate it again uniformly, then you bring it back to rest. Then we are coming with our body back to rest here. So we can see that we have tried to fix every graph here into a single graph, leaving only at the curved when the body was moving with the non-uniform velocity, because with a linear motion, we said we are dealing with a body that are moving in straight line. So that's why you see that we try to combine all these ones that are moving in a straight line in the single time graph. So we'll see that you can even explain your graph here. How is that possible? If you said your body started from rest here, then moved to point A, and then to point B, then to point C, and then back again here to point D. You see that from O to A, if you have OA, the body has uniform acceleration. Now let's look from point A to B. If the body is from A to B, the body attained a uniform. It has uniform velocity. So what happens when the body moved from B to C? From B to C, you see that this one here is another line that is moving upwards, and we say that when it is moving that way, that means that the body has been accelerated again uniformly. So you see that this one here, the body has uniform acceleration. So if you come to B to CD here, the body is coming back to rest. So the body is coming back to the 0 point where the velocity here is 0. So we are bringing it back to rest. So our D is uniform deceleration. So you see that all this has been combined there. So what happens when you're getting the slope of this graph? What will you get? Look at the definition of acceleration. We say that acceleration is the rate of change of what? Of velocity with time. So when the velocity is changing, and you see here it is the velocity actually changing with time. So if it is changing there, that means that when you try to get the slope of your graph, you're trying to get the acceleration of the graph. So you'll just, when you get the initial velocity, you get the final velocity, then you divide it by the whole the time taken for the body to move. You divide it by the difference between the velocity. So you'll come up with the slope, which is the acceleration of the body. So for you to get this graph, the steps you use easily is that the first thing is that you try to divide the whole motion into stages. So you can see that at first we divided the body into the stages. So after dividing your body into stages, what do? You try to obtain the initial velocity of the body and the final velocity of the body. Then if you look at this, how would you attain the initial velocity of the body? And then how would you attain the final velocity? So you'll see that here our body was at rest. The initial velocity is 0. Then the body accelerated to a certain value of this, to a certain value here. Let's call it V. So this value here, it becomes the final velocity with which the body was accelerating. Now, if the body was moving with uniform velocity, what initial velocity was the body given? The final velocity of one body becomes the initial velocity of the other body in another stage. So you see that the moment you attain the final velocity of a body in one stage, it becomes the initial velocity of the body in another stage. So this is how we draw our velocity time graph. But then still you can also find the distance under this graph. How do you find the distance under the graph? The distance of the body covered here, we cannot determine it by this y-axis, because we said here we are plotting the speed with which the body is moving. And then we cannot say that the values here is the distance. No, because here it is showing us the time the body is using to cover that distance. So the distance we obtain here is this space here. The space under the graph, the whole of this, becomes the distance the body has moved. So how do you get this distance the body has moved? You can divide your graph into sections. So you see that when you divide this into sections, you are going to come up with some figures. So when you have that, for example, if we try to, let us make one stage here. When we have this here, we try to pull it down. You see that we have created a figure right here, and which is a triangle. So you see that you can easily find the space in a triangle by getting, if you know the time the body moved from here up to the point when it was to attain uniform velocity, this one becomes the height of your triangle. And then you have the base, which is the time taken for the body to move from O to A. So when you know that, you can use that formula also to find the distance. If not that, you can use the equations of motion to find the distance under that graph. As long as you know, if you have the velocity, you have the acceleration, you know it on the graph, you can easily get that distance. But we are going to look more into that in our next lesson when we come to see how we can calculate our figures, or how we can get the velocity in a time graph, or we can get the distance. We are going to all see that in our next lesson. So this is how we draw our velocity time graph. It is much similar to the distance time graph, but then the difference also is, if you look at this, the slope gives us the acceleration, but with distance time graph, it is not the case. It does not give us the acceleration, but it gives us the speed with which the body is moving. So with this, we come to the end of our lesson for today. We shall meet again in the next lesson.